Hi students, today our topic of discussion is about network theorems. So these are the network theorems we are going to discuss in this module. They are superposition theorem, Thevenin's theorem, Norton's theorem and maximum power transfer theorem. And in this class we are discussing only the superposition theorem. Okay. So all these theorems are valid only in the case of a linear network. So let's start with what is a linear network. So a linear network is nothing but a network in which the parameters in the network do not change with the change in voltage or current. The parameters means the network elements which we are using in that network. So example, the resistance, inductance and capacitors, etc. So if we have resistance, inductance and capacitors in the network, these values does not change with voltage or current. Therefore, we can consider that network as a linear network. So these theorems are valid only in the case of linear network. And in today's class, we are going to discuss what is known as a superposition theorem. Okay. So let's start with a simple network here. So here we have, as you have seen here, two voltage sources are present in this particular network. Okay, two voltage sources are present in this network, and again some amount of current I is flowing through this particular resistance R. Now our aim is to find out the current I flowing through this resistor R, and of course you know that this current is due to the presence of the voltage source V1 and the voltage source V2. And now I'm going to discuss one way of finding or one method of finding the current I which is flowing through this resistance R. So you just first assume that here this voltage source I2 is not active and only this V1 is active. So in this particular case, we can consider that the current which is flowing through the resistance R is only due to the voltage source V1. And let the current can be identified as I1. That is, the I1 is nothing but the current which is produced due to this voltage source V1. That is, voltage source V1 acting alone, the V2 is inactive. Okay, that is, we have a value I1 here. And similarly, as the next step, we just assume that only the voltage V2 is activated and V1 is inactive. Okay, in that case, let the current be I2. So the I2 is nothing but the current due to this voltage source V2 acting alone, V1 is inactive. So now we have two currents, I1 and I2. Okay, we have two current I1 and I2. And according to the superposition theorem, the total current I can be calculated as the algebraic sum of I1 and I2. So now you know what is this I1 and I2. I1 is the current flowing through this R1 which is due to V1 alone, and I2 is the current which is flowing through the resistance due to V2. So according to superposition, the total current I is nothing but the I which is due to the effect of both the voltage source V1 and V2 can be calculated as the sum of I1 and I2. This is the superposition theorem. So the superposition theorem is valid not only for the current and we can find out the voltage also using the same techniques. So we can define the superposition theorem as the superposition theorem states that in a linear circuit that we already discussed, it is valid only for the linear circuit. In a linear circuit with several sources, that is, the network consists of more than one source. With several sources, the response for any element, here the response means nothing but the current or the voltage related to a particular element in the circuit is the algebraic sum of the response produced by each source acting alone. That is, if there are two sources, First, we need to find out the response of a particular element. The response can be a current or a voltage. The response of a particular element due to first source and then the second source and so on, and add it together. That is the algebraic sum of the response produced by each source acting independently. So now the question is, if there are more than one source, how we can deactivate the particular sources? So usually what are the sources we are using? They are voltage source and current source. So if there are more than one sources in that network, so in order to use the superposition theorem, we need to deactivate all other sources and keeping only one at present. So now let us see how we can deactivate the sources. So let us first see how we can deactivate the voltage source. Okay, how we can deactivate the voltage source. So here you can see a voltage source, and this voltage source can be deactivated by replacing the voltage source by a short circuit. So in the case of short circuit means the voltage does not exist in the short circuit. So how we can deactivate a voltage source? A voltage source can be deactivated by replacing the voltage source with a short circuit. So here we can have another example. A voltage source and a resistance is there. If you want to deactivate, just replace this voltage source with a short circuit. And similarly, if we have a current source, and how we can replace that current source? So if a current source is present in the circuit, it can be replaced with an open circuit, or we can deactivate the current source by replacing the current source with an open circuit as shown here. So here is a current source. It can be deactivated by replacing this current source with an open circuit. So in the open circuit, there will not be any current flow. Okay. So the voltage source can be replaced by a short circuit, and in order to deactivate the current source can be replaced by a open circuit. And this is the superposition theorem. So one more time, the superposition theorem states that in a linear circuit with several sources, the response for any element in the circuit is the algebraic sum of the response produced by the individual source acting independently, or the source acting independently. That is the superposition theorem. Okay, we will understand this more after doing an example problem. So let's come to an example problem. Here the question is, determine the current flowing through a 10 ohm resistor using superposition theorem. So this is the given circuit, and this is the 10 ohm resistor, and here the current also mentioned as I in this direction. So everything is mentioned here. So we need to find the current flowing in this direction through this resistance 10 ohm. Okay, that is the question using superposition theorem. So just have a look into this network. Here we have more than one sources. That is, here we have two sources, and they are the 100-volt voltage sources and 5 ampere current source. Okay. So as you know, the voltage source can be deactivated by replacing it with a short circuit, and current source can be deactivated by replacing it with an open circuit. Okay. So as a first step, the case one is 100-volt voltage source acting alone. So case one, the 100-volt voltage source is acting alone. That means we need to deactivate the current source. How we can deactivate the current source? By replacing it with a open circuit. So we can deactivate it with an open circuit. That open circuit means there will not be any current flow. So in this case, in order to find the current flowing through this 10 ohm resistance, first we need to identify what is the total current IT. So the total current flowing through this network is nothing but the voltage applied is equal to V by R. The voltage applied divided by the total resistance. So in order to find the value of this IT, first we have to find the value of the total resistance. So for finding the total resistance. Okay, here you can see that this 10 ohm resistor and 30 ohm resistor and 20 ohm resistor are in series after replacing the current source with an open circuit. So this is in series, and we already studied that if the resistance are in series, the effective resistance is nothing but the sum of all the resistance in the series part. So in this case, the equivalent resistance is equal to 10 ohm plus 30 ohm plus 20 ohm, that is equal to 60 ohm. Okay, and therefore we can replace these three resistance with a single resistance of value 60 ohm as shown here. So this 3 ohm resistance are replaced with a single resistance 60 ohm. Okay, now again in this circuit, again you can see that these two resistance are in parallel. The 60 ohm resistance and the 30 ohm resistance are in parallel. So how we can replace the parallel resistance? In effect, the effective resistance when the resistance are connected in parallel are, if two resistors are connected in parallel, then the effective resistance are R1 R2 divided by R1 plus R2. Okay, so R1 R2 divided by R1 plus R2 in this case, that is equal to 20 ohm. Therefore, this two resistance combination in parallel can be replaced with a single resistance 20 ohm. So now this is the total current IT. These two resistors are in series. So the same amount of IT will flowing through this resistance. So this IT can be found out by using the total voltage divided by the total resistor. So that is equal to 100 ohm divided by 30 plus 20, that is equal to 2 ampere. That is, what is this total current IT? That is equal to 2 ampere. So problem not yet finished. We have to find out this I1. Okay, what is this I1? I1 is the current flowing through this resistance. Why it is termed as I1? Initially it was I. Now why it is I1? That is here now we don't have this current source. We have only voltage source. So the current due to this voltage source is represented as I1. Then how we can find out this I1? The total current coming from here get divided into 2, and some amount of current will be flowing through this path, and some amount of current will be flowing through this path. So this is the current we need to identify, the current which is flowing through this path, this resistance and this resistance and this resistance. Okay, and again this we can assume that the current will flowing from this to this, so A to B, the direction of current is from A to B. So these two combination can be considered as a parallel combination. That is, this resistance and this 30 ohm resistance and this resistance are in series, and this combination is parallel with this 30 ohm resistance. So this is having a parallel combination. In the parallel combination, we can find out the current flowing through any one of the resistance path using current division rule. So here we have to find out the current passing through this path. So what is the equation? The total current multiplied with the resistance in the opposite path divided by the total resistance. Here the total current is IT, and that we already find out as 2 ampere. So I1 is the current flowing through this path is equal to the total current 2 multiplied with the resistance in the opposite path, that is 30 ohm divided by the total resistance, that is equal to 0.66 amps. In which direction? From A to B. That also we need to identify. Then only we can calculate the algebraic sum. So I1 is equal to 0.66 amp in A to B direction, or in the direction from A to B. And let's go for the case 2. In the case 2, only 5 ampere current source is acting. That is, we need to deactivate the voltage source. So how we can deactivate the voltage source? We can deactivate the voltage source by replacing it with a short circuit. Okay, this is a short circuit. So again, then just let us see, we have only one current source. So the direction of the current source is already mentioned using this arrow. And this current, what happened to this current? This current will reach here, and at this point it will divide into 2. Some amount of current will be flowing in this direction through 10 ohm resistor, and some amount of current will flowing in this direction through this resistor. So what happened to the direction of this current? This current will be reversed. This current will be in this direction, and let the current will be equal to I2. Why? Because it is I2. Here we have only current source are there, we deactivated the voltage source. So current due to this 5 ampere alone is termed as I2. So now our aim is to find out the value of this I2. So again, in order to find out the value of I2, we need to reduce this network. So here you can see that this 30 ohm and 30 ohm are in parallel. So we can replace it with the effective resistance, that is equal to 30 R1 R2 divided by R1 plus R2. So both the resistance are same. 30 multiplied with 30 divided by 30 plus 30, that is equal to 15 ohm. Okay, that is this two resistance combination is replaced with the 15 ohm, and this 100 ohm resistance is there as it is, and this 20 ohm resistance is also there as it is, and this 30 ohm resistance is also here. So here you can see that the current is flowing from B to A. Okay. So the total current 5 ampere. Here the total current is 5 ampere. It is coming at this point and it is split into 2, and some amount of value, say I2, is flowing in this direction and some amount of current is flowing through in this direction. So we have the total current and we have two paths for the current. One is this path and one is another path. So here we need to find the current through this path. So using current division rule, you can find out the current through this path, that is equal to the total current multiplied with the resistance of the opposite path. So 30 ohm divided by the total resistance. So this 15 plus 20 plus 10 plus this 30. So we get that is equal to 2 ampere. But here the thing we have to take, we have to consider is this, the 2 ampere will flow from B to A. So in the first case, that is when the voltage source is acting alone, the current is 0.66 ampere, that is passing from A to B, and here it is passing from B to A. Okay. So both the current are in opposite direction. So while taking the algebraic sum means we need to take the subtraction instead of addition. So the total current I can be, I using the superposition theorem, I is equal to I1 plus I2. So I1 is I1 in A to B direction. So and again we are asked to find out the total current I in A to B direction. So we take this I1 as positive. So I1 plus I2 is equal to 0.66 plus minus 2. Why it is minus 2? This is from B to A. That is why I taken the minus sign as minus. So 0.66 plus minus 2, that is equal to minus 1.34 ampere from A to B. Or we can write this is equal to 1.34 ampere from B to A. So in this way you can find out the current through this 10 ohm resistance using the superposition theorem. So what we did for this, first we deactivated 5 ampere current source, then find the current I1 through the 10 ohm resistor, then we deactivated the voltage source, and then we again find out the current I2 which is flowing through the 10 ohm resistor. In both the case the direction is different. So we find out the total I is equal to I1 minus I2, that is equal to 1.34 ampere from B to A, or if you want to consider this as an A to B, we just taken that as is equal to minus 1.34 ampere. Okay, now we have a practice problem here. Find the current I, which is I flowing through this 10 ohm resistor in the network given below, and also find the voltage across the 10 ohm resistor. So here we need to find out the two response, one is the current and one is the voltage. So using the superposition theorem, first you find out the value of this I. After getting this I, directly you can find out the voltage drop. How we can find out the voltage drop? V is equal to I into R. After getting this I is get multiplied with this 10 ohm, then you get the voltage V, that is equal to I into R. So the similar method you can use. First you can deactivate any one of this source and find the current through this resistance using the other source, and as a second case you just deactivated the another source and find the current I2. So take the algebraic sum. Okay. So that is about superposition theorem, and so with this I am winding up this particular section, and thank you.